Okay. I'm going to be talking to you today about meta-analysis. And I started out writing this talk thinking I was going to concentrate on assumptions that are sort of hidden from us when we're often doing analyses, things that we don't think about, and how it might impact our results and our interpretations. But then I thought, you know what, that's kind of technical. I think I would rather focus on the things that people have asked me in consultations in the last 5 years or so. We've gotten lots and lots of, since pandemic, lots of people coming to us asking for help and meta-analyses. And so I felt to people, at the very beginning and through the whole process of doing their analyses, through responding to reviewer comments after they've submitted them. So I thought I would address a few of the things that seem to keep popping up, the different types of questions that people have, and make this a very non-technical talk. So there's very little, even like, computer output stuff in this talk at all. It's all about thinking about what you're doing and being very careful and considerate about the decisions that you make. Come on. So first of all, what is it? This is a really sort of simple breakdown of the goals of meta-analysis. It is part of a systematic review of literature that has a couple different aims. So first of all, they want to synthesize results of primary research, so research studies that are actually, performing the studies, gathering the data, publishing them, using explicit and reproducible methods. This goes along with lots of guidelines that the different organizations have put out and how to perform systematic reviews. And I encourage you to look up those different guidelines. There's, the Prospero statement, there's Strobe statement, there are all these different guidelines, and also to investigate registration of your plans for a meta-analysis. That's a really good thing to do as well. This is the systematic review of a systematic review and meta-analysis part. And it's often aimed at answering questions like, is an intervention effective? Versus, conventional or as is type of treatment. Does this new drug treatment work better than current methods? And so it's answering a question like that. Yes, yes, it does. And we have all these studies that say it does. But it also aims to produce a quantitative summary of the evidence through statistical methods. And so the additional information that you get from this meta-analysis part of a systematic review is what is the magnitude of the effect that you're interested in. So what is the treatment effect of the drug? Does the systolic blood pressure decrease more for those on this drug than, this other conventional approach to maintaining good blood pressure? And these are some basic steps depending on, whose article you're reading about how to perform a meta-analysis. They might change somewhat, but these are the basic things that you need to be thinking about as you go through the process of a systematic review and meta-analysis in general. And you can sort of separate them into the review steps and the statistical steps. I am a person who does lots of statistical analysis, so you'd think I'd be like really into steps 5 through 8, but I'm actually really into some of the steps in the first part. And I'm going to talk a lot about step number 1 and a little bit about step number 6 and 7. So formulation of a study question, lose. Pooling the data by applying specific statistical techniques. I'm not going to go into this very much, but there are some basic things that sort of pop up a lot in our consultation. So I'll talk a little bit about those. And then investigating sources of differences between studies, specifically looking at bias, rather than looking to apply meta-regression or subgroups of analyses. I'll be talking about different methods of assessing bias. So I'm going to talk about knowing your research question and how to get that and formulate it, how to choose your analysis model, or some things to think about when you're thinking about the actual statistical part of the meta-analysis, and assessing bias. So formulation of a study question. The reason why I am focusing on this, well, first of all, it's the first step. But as a person who talks to lots of different people about lots of different research topics, the first question I ask when I'm meeting somebody for the first time is, what is your research question? It is so fundamental to any research project that it doesn't matter what we're looking at. That is the first thing that I need to know before I can help you. And this is no different. And in fact, if you are able to formulate a good study question for your systematic review and analysis, it's going to help you get to a really good quality product or result. So this is why I'm focusing on this. It is absolutely fundamental to everything else that you do in your meta-analysis. So I absolutely encourage you to spend a lot of time really considering what your research question is. And there are lots of different tools that help you formalize this process. One of the most common is called PICO, and it helps you define your population of interest that you'll be doing your review on, identify the specific intervention. This is obviously aimed at experimental RCT type of research or case control type of research, where you have two groups that you tend to, that you're comparing. So you need to define what the intervention that you're interested in is, what the control or comparator group is, and define your specific outcome. And like I said, there are lots of other tools available to help you do this, like PICOS, which is obviously based on this, and then has one extra sort of criteria or guideline, or SPIDER, there's ECLIPSE. There are all these acronyms aimed at getting you to think about specific aspects of a systematic review that may or may not actually be all that relevant to your specific situation. And in fact, the PICOS and SPIDER ones have guidelines that sort of expand the research question in order to include more qualitative research. So if you are doing a review where you want to include more qualitative publications, those might help you define your research question better than just the PICO guidelines. One thing to remember is that your particular goal may not be captured in these specific letters. So like I said, this is aimed at RCTs, comparing one group against another, but that's not all you have to do, or all you can do with a meta-analysis. You could be looking at getting an overall estimate of correlation between two variables or something like that. Or and that's not a intervention and control group comparison, obviously. So just because it's asking you to define an intervention or control, that's not very helpful when you have that type of situation. So you can sort of tweak these suggestions so it better fits your research goals. But I do encourage you to use these tools to help you focus. So for example, say we have Isabel. Isabel is a researcher. She's studying the effects of domestic violence on well-being, and she decides to do, as part of her PhD, a systematic review and meta-analysis as her first project. And she wants to know about the effectiveness of advocacy on the outcome. So to focus her topic, she uses the PICO approach to formulate a really focused research question. So she might say, okay, the population is women who have experienced domestic violence. So that's who we're going to be looking at. So she might restrict her lit search, or it included her inclusion criteria that the sample has to be women 18 years old or older, something like that, and who have experienced domestic violence. Then she's talking about an intervention, which are advocacy programs. So perhaps there's a bunch of research on different approaches to, as community outreach, or in different ways in which people experiencing domestic violence can access help. And comparing them against the control group, which is either routine treatment or those people gaining help through general practice, talking with their doctor, things like that. And then finally, she has decided well-being is going to be the quality of life as measured by the SF-36 scale. Now, this is a pretty specific outcome, which is really great because it leads very easily into stating, what the outcome variable is when you do your literature search, and that's really great. And it's also a good choice because SF-36 is a very, very widely used scale. So she's not limiting her inclusion criteria too much in order where she's only going to get 2 or 3 studies in which to include in her review. So in this process, she can refine her research questions. So based on her answers to each of those criteria, she says her research question is, for women who have experienced domestic violence, how effective are advocacy programs as compared to routine general practice treatment for improving women's quality of life as measured by the SF-36 scale? It also can guide your objective statement that you might be putting into your review, and maybe even your title. So you could, just using that tool, you could get all the way to your article title if you are specific enough with your responses to those questions. So I want to emphasize how important it is for you to know what your research question is in a systematic review. It's important in any research project, but I think for a systematic review, it is especially important because, and as somebody who has not actually collected the data for systematic review and meta-analysis, I see the amount of work that comes out of it. And it is massive. It is so much work, so much time, so much collaboration, so much communication with other people to try to get as much information as possible, that having a very clear idea of what you need is going to keep that workload down as much as possible. And it's not going to, you're not going to end up sort of, wandering off, on a little tangent. Maybe somebody has, uses a, EQ5D as their well-being measure, but you've already said, no, I'm just looking at the SF-36. So, very interesting, but at the moment, that's not really what I'm interested in. Yeah. So if you have a really good research question, you will be able to define your inclusion and exclusion criteria much more clearly. If you don't do that, you're unlikely to be able to aggregate study effects into a meaningful summary of an overall effect, because you're just going to have so much variability in the information that you extract from the studies. And you can't really end up with a quality analysis. So I very much encourage you to spend a good amount of time thinking about what the research question is and provide yourself a really good pathway for finding those relevant studies. Yes.
Question.
Yes.
You might want to take that step.
Okay.
Can meta-analysis be done on correlations between characteristics for a specific population?
Can meta-analysis be done on correlations between characteristics of a specific population? Yes. Yes, you can. If you have measures of your two variables or however many variables you're interested in, and you have enough studies in which to do a quantitative aggregation, yes, you can meta-analyze correlations. A few other things to think about as you are formulating your research question that the PICOS, SPICE, or Eclipse acronyms don't really point you to, but you do need to think about things like study design. It can be difficult to find a common effect size from studies that have different designs. For example, if you have some studies that are RCTs, and then you also have studies that are case controlled, depending on what your outcome measure is, it may be very difficult to find a common metric in which to aggregate over. That doesn't mean that you can't do a systematic review and meta-analysis with both of those, but you might need to think about, do I need to separate our RCT studies from our case control studies and then get aggregate estimates for those two different study types. So if that is something that you may run into, think about whether you'll be able to or likely to find a common metric for those different study designs. Then I have, should you limit the time frame? And I realized just an hour ago that question can actually be interpreted in two different ways. So first, I noticed that the PICO thing didn't really have a specific, explicit question about sort of time in your outcome. A lot of RCTs have follow-up in a year or 2 years, but a lot of research that is looking at the same types of questions have different timescales in where that final outcome actually is. So do you need to put in your research question, is there a difference in well-being for women experiencing domestic violence 12 months after having participated in this advocacy program versus regular care? Should you limit the time frame, could be within the studies that you are aggregating over. It could also be the studies that an inclusion criterion. So you could be looking at the whole body of research on women and domestic violence, and the studies could go back to the 1930s, 1920s. You probably want to limit your inclusion criteria to maybe the last 10 years or something like that. And make it so that you don't have tens of thousands of studies and sets of results that you're actually looking at. The trick here is to define your search criteria enough so that you are able to perform a thorough review of the literature and aggregate meaningful data, but not so much that you end up unable to identify enough studies that fit your criteria. Yeah, so sort of a pressure there. Hopefully thinking very carefully about that formulation of that research question sort of finds you right in the middle of those two things. Now, moving on to the statistics part. I talked to, so I spent a lot of time on the research question because I think it's so important. And I'm actually going to be spending so little time comparatively on this. So, it just, this part in particular is, it's an important distinction in the model in which you choose to analyze your data. But it's not particularly interesting, but it is something that people ask all the time. So when you're first learning about meta-analysis, you get lots of information about a fixed effect versus a random effects meta-analysis. And so these are the sort of the philosophical differences behind them, which actually do translate into some statistical differences, but I'm not going to, concentrate on that too much. So what are the differences here? So with the fixed effect meta-analysis, we're assuming that there's a common treatment effect, so that advocacy versus, general practice effect is constant across all study settings in our meta-analysis. And any differences that we see from one study to another are based on random sampling error only. And the summary of a treatment effect in the fixed effect model is a weighted average of those study-specific effects. And those weights are determined by the inverse of the variance of the study effect size. So that's almost as technical as we're getting in this talk. A random effects meta-analysis assumes that effects do vary from study to study. We're not all just estimating the exact same thing, and differences between studies are random error, that random sampling error, plus variation in true treatment effects. So it's sort of got a different idea of what that variability between studies is, so that those weights that we apply to each study effect size are based on that random study variance and another component which represents heterogeneity. And what are the implications of these? Well, first of all, the fixed effects and the random effects will give you similar results when there is little heterogeneity, because that extra little term in that random effects estimate is very, very small. So when there is little heterogeneity, these two should give you quite similar results. The other thing that comes out of that is that for random effects meta-analyses, the random effects estimates are it's more influenced by small studies compared to a fixed effect meta-analysis. And the random effects meta-analysis is more conservative, meaning the confidence intervals around that aggregated effect are larger. But so we have these philosophical differences, and that translates into some computational differences. Yes.
Okay, just trying. Fixed effects are where you're comparing samples.
Yeah, and you're assuming they're all estimating the same treatment effect, and that any differences, it's only random sampling error.
So is it related to think of it as within subject?
What are we talking about within subjects?
Because I do.
Mhm. Right.
Treatment error.
Oh yeah, it's sort of, yeah. What's that? Yeah. Oh yes, yes. The question is, he's trying to understand what the fixed effect, assuming the common treatment effects and the variability around the different study estimates. So I'm going to say yes. I think that you're right in that they're all. It's sort of like when we're talking about a sampling distribution, how we talk about, imagine if you were able to do this experiment 1,000 times and calculate the mean. It's sort of like what this fixed effect, these assumptions are talking about. They're saying, imagine that there's one treatment effect and these are all manifestations of a random sample. And we're estimating the mean. That's sort of what's going on here. Whereas the random effect one says, yes, there's that, but also there is this extra notion of variability as well. And that extra notion of variability can be, systematic differences that you're just not thinking about yet. Or things that you don't have any idea what's going on. Yeah, why there's variability. Okay, so we have these philosophical and statistical differences on the fixed effect and random effect model, but I will say that I have never done an analysis where we preferred the fixed effect model, just because I don't really think that studies are all that similar. There's a lot of variability in how they're conducted and the measures and the populations and stuff. So I actually think that the assumption that there is no heterogeneity to be untenable, and as do these people They say the majority of meta-analyses now report random effects results, and those that report only fixed effect results should be viewed with skepticism. It's like, just like, you know, really? That's a really strong assumption. Especially those that report pooled treatment effects with marginal statistical significance. I don't like the term marginal statistical significance, but, you know, basically, you know, you're probably putting too strong of an assumption if you're reporting fixed effect meta-analysis. Although I do have to say that twice I have had to respond to reviewer comments. Why didn't you do a fixed effect analysis? My answer is like, well, I don't actually think that they're all the same, you know? Okay, so here's something that's a bit more practical. Software considerations. A lot of meta-analyses you can do a really great analysis using a specific purpose-built software, which is pretty easy to use, particularly for people who are not comfortable with doing statistical analysis. So you have RevMan, you have comprehensive meta-analysis, and both of those are available for you to use online, although I think you might have to pay for comprehensive meta-analysis, CMA. But there are other ways to analyze these data as well. And for in terms of general statistical software, R, Stata, and SPSS. SPSS is a new meta-analysis component to it. So you can do lots and lots of different high-quality analyses in any of these. Having said that, there are lots of meta-analyses that the purpose-built software and SPSS are not really good for. They're really good for those straightforward intervention versus control comparisons, for continuous outcomes, and for binary outcomes, and for aggregating and getting an overall odds ratio or rate ratio. But as soon as you add too much complexity, they can no longer give you what you want. And so I would encourage you, even if you've never really done any statistical analyses before, to remain with your research question. Do not change your research question to fit what your chosen software will allow you to do. Once you have your well-formulated research question, keep it well-formulated. It's a reason why you landed on that research question. So keep it that way. And if it requires you to stretch a little bit and learn a bit more coding, such as Stata or R, which do have the facility for expanded, more generalized models, that is only going to help you. The experience of coding and understanding a more complex model is really good for you technically, and it's also really good for actually answering your research question. Another thing to think about in your analysis is sometimes you may have more than one outcome in a study, and it could be more than one measure of well-being. So I imagine Isabel's going to find that she did limit her research to SF36, but she's probably going to find that a lot of research also has something like the EQ5D and the well-being scale, and they're all different measures of well-being. And maybe instead of just focusing on one, she actually does want to look at more than just the SF36 quality of life scale in her meta-analysis. But what do you do when you're getting the same, you're getting multiple outcomes from the same study? Or maybe that a particular study has more than one intervention group. What do you do then? And so you've got a couple different estimates of how an intervention might differ from a control. Or maybe you've got results from more than one follow-up occasion. And if you haven't really specified, hey, I'm only looking at the 12-month thing, maybe you're able to use more than one measurement occasion in your data analysis. But we can't assume that those measures that are from the same study are independent. And so we do have to do something about that dependency. We must address it somehow. And there are a number of different approaches that we can use. The reductionist approach, this is trying to make it as easy as possible for the person who's doing the analysis. And it boils down to, hey, let's try to keep it down to one effect per study. So how do we do that? Well, first thing we can do is aggregation, and it's basically just averaging effects to get an overall effect for each study. And you know, as a person who deals with dependent data a lot, I was like, oh my God, why would you do that? It just it hurts my heart. So then I was looking at other options, and there are subgroups. So if you have a couple of different estimates from the same study, but they're actually from, you know, maybe you have males and females or something. So you can do you know, an estimate for the male effect and the female effect or something like that. So you might have more than one effect from a particular study, but when you're actually aggregating, you are just considering one value from each study. But sometimes it's not quite that clean. And so you can also do what's called the shifting unit of analysis, where you try to do the subgroups as much as possible, but sometimes you still have subgroups that have more than one effect. And when you get there, then you average those two. So sort of a, you know, combination of the aggregation and the subgroups strategies. Then there's the integrative approach, and these are full models which allow you to model the correlation due to being from the same study. There are a few different ways that you can do this, and you can do multivariate meta-analysis, where you have more than one outcome that you are analyzing at the same time, but it does require knowing the correlations between different effect sizes from each study. And that is usually not reported. So it can be really difficult for this type of approach. Instead, you can do what's called robust variance estimation. And that sort of adjusts the estimates of variance and sort of does an implicit control of the correlation between those repeated measures. Or you can do a multi-level meta-analysis where you're explicitly including a term for the correlation of those repeated effect sizes within each study. Now that's where I would go. That's what it'd be like. I would choose, be like, oh yeah, definitely we're doing a multi-level meta-analysis of this. Absolutely, this is what we're needing to do. But I just learned a few days ago that you actually don't have to. Depending on what your intent is, you can actually just do aggregation. And it actually is mathematically equivalent under certain circumstances. So I learned that my pearl clutching, the aggregation approach, is a bit dramatic. So just because you do have some studies that might give you multiple outcomes in your meta-analysis does not mean you have to increase the complexity of the meta-analysis, and you can keep it as simple as possible. I would very much recommend that you take a look at this reference, the full reference I'll have at the end of the slides, about when it is appropriate to do that aggregation, and it keeps it a little bit easier. And then also refer to your research question. That's going to help you with this, making a decision about how to handle these multiple outcomes. Okay, so moving on. Moving on, I'm going to be addressing one source of bias. This is the most common way that people are talk about sort of probing the overall estimate in meta-analysis for bias. There are lots of different kinds of bias, but publication bias or reporting, which is sort of a subset of reporting bias, that is by far the one that people are concentrate on most. And I think it probably has the most different approaches of how to look at it. But it's not the only one. And there are different kinds of bias that are relevant to different types of meta-analysis. Like there are a few different types of biases that are important for meta-analyses and genome-wide assay meta-analyses that aren't relevant to other things. So it's really sort of, if you are doing a meta-analysis in a very specific area, you might have to be concerned about other types of bias as well. But like I said, that publication bias, some people call it a small study influence bias, is by far the most common one to report on and consider. Okay, so what is reporting bias, of which publication bias is one example. Reporting bias occurs when the dissemination of research results is influenced by the nature and the direction of the results. And this is not just in whether or not a journal decides to publish something. I'm talking a person runs a study and finds a null effect. And they're like, well, it's not worth even writing up. I'm not even going to send in an abstract, so it can start from the very beginning. This influence of the direction and size of effects. But publication bias is what most people talk about. But reporting bias is really sort of a full, research, area problem. So what are the statistical treatments for assessing publication bias? The first one, I'm sure that you guys have seen this before, is called a funnel plot. And it is a plot of the individual effects that you have in your data by some sort of measure of the variability. So these are showing the standard error, and you can see that the y-axis is flipped so that we have a nice funnel going down. And this first one, the one on the left, we can see that with the most of our effect sizes are clustered up in the middle of that triangle. We have one dot way down in the left corner. And what people often interpret this as is saying is that we have one study that has really high variability, which often goes along with the fact that this study having a very small sample size. And that also goes along with the fact we know about it because it's got a massive effect size. And you can see that it's really large effect size relative to everything else. And the reason why this is important is that smaller studies require massive effects in order to get that p-value less than 0.05, which means that a small study that's published that has a p-value less than 0.05 is probably showing an exaggerated effect size. And that's what they mean by a small study bias. So that small studies tend to have large variability, and if it's been published, it's probably a huge effect size and maybe not representative of what's actually happening. Because those small studies that have small effect sizes or p-values that are larger aren't really published as much. So what this is telling us is that we may have one study here that is influencing our odds ratio a bit too much because it's probably too big. Now, the other funnel plot that we have here is, it gives us a little bit more information. It's got the same scatter dots and stuff. And you can see that the funnel is shifted over a little bit with the middle part on the null value of 0. And we have these colored bands, and this gives us an idea of what those p-values for each of those studies are. So if we have the dots in the middle of the white, we know that the p-value is above 0.1 or so, all the way up to 0.99. Then we have the blue band where the p-values are between 0.05 and 0.1. And then the other ones that show those smaller p-values. So, but we still get an idea that, wow, yeah, we still have that one study that is really quite different from all of the rest. But it doesn't, it's not quite as easy to see any asymmetry. So what what you should be seeing in a funnel plot that shows no evidence of publication bias is it should be symmetric. You should have small study estimates all across the range of positive and negative effects. So you don't want to see any evidence of asymmetry in your dots here. But this is just a graphical representation of it. We do have a statistical test that goes along with it called Egger's test. And it's very easy. It's pretty much always, available in any meta-analysis package. And we can see we have a p-value 0.0031, which we would interpret as saying, oh, we have some evidence that we have funnel plot asymmetry. There's some bias here. And I don't want you to jump. I would encourage you to not jump to the conclusion you got small study bias or publication bias, because there are lots of other different kinds of bias. This is simply maybe our estimate needs to be probed and do some sensitivity analyses. Yeah. So another thing that we can do is sort of get another estimate of our treatment effect if we didn't see that asymmetry. So you can see this funnel plot now has some dots that are not filled in. These are hypothetical studies. If we were able to see a symmetric funnel plot, the dots both sides and showing our small studies with the really high effects, but on the other side, what would our estimate be? And this funnel plot is just saying, yeah, it looks like we have, we would need about 4 studies that would balance things out. So if we had those 4 studies with these effect sizes and variability, what would our updated effect estimate be? And we can run another analysis basically where it tells us, oh, hey, I'm adding in 4 studies, and we get an updated estimate down here. And you go, now I can't see the full estimate. The full estimate, oh, there we go. The original aggregated effect was negative 0.803, and our updated one is it's been sort of shrunken a little bit, which you would expect, to negative 0.71. So this is just one way to sort of go, well, maybe if we didn't have that one small study with that really large effect size, we had other things that were showing, opposite effects. What would our estimate be then? And we can report that. Those are not the only things that we can do. There are actually even more involved statistical treatments of this. PET peas, limit meta-analysis, T-curves, and then selection models. And each of these get a bit more complicated and a bit more difficult to understand and harder to interpret. But they are available, and they all will end up giving you some sort of estimate, an adjusted estimate of your treatment effect, and those are all be different. So, have fun looking at all of those and trying to figure out what's going on. The thing is, though, nobody knows what the best method is for looking at publication bias or reporting bias. Nobody really knows. There's been a lot of research out there looking at the performance of each of these models in different situations, and there's no clear winner. Some are good sometimes and not so good at other times, but they all are not great when you have high heterogeneity in your analysis, and they're not great with a small number of studies. So if you have fewer than about 10 studies or so, none of these are going to be all that great, and you're going to just be left with probably looking at some of those funnel plots and going, well, I guess there might be a little bit of evidence here, and because that's all that we have. And each of these can under or overcorrect. And as I mentioned, some of them are really hard to understand what you're doing and how to interpret. So they may not be all that user friendly, even if they are, you know, have good statistical grounding. If this is something that you really need to include in your meta-analysis, I would encourage you to do a lot of thinking and get some help, because these are kind of hard. And also, you probably want to rely on more than one method. Okay, so now I'm just going to sort of give you some very quick overviews of other types of meta-analysis models that you may consider and may be appropriate for your particular question. Meta-regression, this is a way to examine how study level factors may influence heterogeneity. So if you do find that you have some heterogeneity in your effects, you can probe it with some hypotheses that you might have. So if you have studies over a large time period, maybe you can put in year as a predictor and see if the effect sizes are dependent on year. You can do meta-analytic structural equation models, which is really quite complex. But if you have something like a mediation hypothesis, anybody who does research in behavioral sciences, psychology, management, they use a mediation and indirect effects models all the time. And you can actually do meta-analysis for a mediation hypothesis. So that's pretty cool. Network meta-analysis, sometimes you're looking at, you're doing research in an area that has more than one type of intervention often. And so lots of research might have an examination of intervention 1 versus control group. You've got some studies that look at intervention 1, 2, and 3 against a control group. And you've got some studies that look at 2 and 3 against a control group. And so you might think, oh gosh, I can only do subgroups analyses on these. That's not true. You can do network meta-analysis, which then gives you aggregates direct and indirect tests of the different interventions against each other, not just against a control group. And so that's pretty cool. And then you can do Bayesian meta-analysis, which will allow you to do, you know, the very simple analyses and also some very complex analyses in a Bayesian context. Okay, so wrapping up, doing a meta-analysis is a lot of work. It is a lot of work. And I have so much respect for people when they come to me with their very nice data sets that they've worked so hard to get. It is, I think that the idea is that, oh, I'll just, you know, I'll find my, you know, results table, I'll extract my data, put it in, and I can go. But no, that it is so much work and so much time to get all of that together. So if you do decide to do a meta-analysis, give yourself plenty of time to do the systematic review portion, because if you don't do that well, then the statistical portion isn't going to give you anything. So make sure that those first 4 steps, you give as much care and attention to as it really requires. And I think sometimes, gosh, my part is so much easier than the data collection part. So if you do stuff, just tell, I'm really impressed with the commitment that you are showing when you embark on this type of analysis. Get some help with the analysis, even if it's just to have somebody go, yeah, it sounds like you're on the right track. And RevMan is totally fine for you to do this. You can do this. Or, oh, you know what, we're going to have to move to R because you can't do, you're going to have to use a generalized linear mixed model here approach to analyze these data. And we can do it. We can help you. And always, whenever you're having to make a decision in this process, keep in mind what your well-formulated research question is. And that's going to help you a lot to not get distracted and off track. Okay, thank you very much. I want to point out that I'll put up these slides, and there are many pages of references and resources for you to help get you going and help answer your questions.
We have one question in the chat.
Yeah.
Would you advise conducting both fixed and random effects, regardless which model may be considered more suitable?
Oh, yeah, you know,
Can you repeat?
yes, the question is, would you recommend doing both the fixed effect and random effects analysis regardless of what you think is more suitable? I want to say no. I wouldn't want to, because I think the fixed effects assumptions are too strict, and it's not what you're going for. That is not an acceptable answer oftentimes to reviewers, and sometimes it'll be fine. A fixed effect model gives you this. I really hate saying that, well, sometimes you just have to, but sometimes you just have to. Yeah. But my heart is saying, no, it's a random effects model. That's, there's no point in doing the other one.
If there are probably was one thing others want to thoughts too. So one thing I always wondered about is why do people always focus on inverse variance weight when you could do inverse of the square root of sample size, which is then you're taking care of sampling that way. Because another type of bias might be well, I'm going to upweight studies that have less variance, but sometimes a study can be perfectly good, just with more variance. I'm going to downweight it. And that might just seem a bit unfair. Mm-hmm. So I just think, like, why don't we use like inverse weight by square root of n, or by say inverse standard error? Mm-hmm. I still don't get why inverse variance weighting is considered the gold standard. Yeah, you guys think about that. Yeah.
The question was about why, when we're weighting studies, are we focusing on inverse variance when there are other types of weighting that we can do. I think that is probably an artifact of technology. It's probably been that's how it's been done. That's what was easiest, and sort of just gone on as the default. But things like I can't speak for Revman and comprehensive meta-analysis. They probably can, but I can't say for sure. But definitely the conventional packages in R, Metaphor, and Meta will allow you to choose a different weighting method. So you are not fixed into that one. It just is the default, and most people don't think about defaults.
Just to follow up, slightly different, but if you can extract the raw data from studies instead, do you think that's a better method generally, especially when we're looking at like primary outcomes where the event rates can differ a lot? And so maybe use GLMM with like a random effect for each study, where the study comes from, and then just use the raw data. What do you think about that?
Question is, if you were able to have the individual data from the studies, would it be better to use the individual data from each study and do some sort of mixed model rather than aggregate? From my perspective, I would say, yeah, I probably would do that using some sort of mixed model with appropriate distribution and set up the random effects correctly. I would probably do that. But having read that, this article, what's his name? There we go. Kostojovsky and Chen. I don't know if that will. Sometimes it's not going to gain you anything, and it is definitely more complex in terms of analysis, but it may not actually give you anything else. Yeah. So So I'm stuck here going, of course I would, but also going, well, that would be silly, because sometimes you don't have to.
We have two more questions.
Yep.
in the chat. I'll just read them out together. The first one is, how long does a systematic review and meta-analysis usually take?
Oh,
And the next one is, how is the power of the random effect model related to heterogeneity?
okay. So how long does a systematic review and meta-analysis take? Okay. I am typically involved in the meta-analysis part. I am not in the systematic review part. But I would say you're going to be, depending on your subject area, the number of articles you have to go through, you're probably going to be in that systematic review part for at least 6 months. Yeah, so like I said, give yourself plenty of time for that. The analysis part, if it is a straightforward analysis, you could be done, relatively quickly. I'd say maybe a month if it's just, that standardized mean difference. So, getting your estimate and then, checking your assumptions and looking at your publication bias and making a nice, pretty forest plot so that everybody wants to see anyway, take about a month. But I will say, I've helped one a student who's doing meta-analytic SEM, and we've been working on it for a year. So, so that analysis part can take a long time too. And then it was okay. Okay, yeah, so when I said random effects estimates will be more conservative than a fixed effect estimate, that means that the confidence interval around that aggregated effect is wider. And if that effect size is close to the null value, you may find that now your null value is contained within that confidence interval, which means that you are losing a little bit of power, but you are not relying on obviously untrue assumptions. So you lose a little bit of that power, but it is actually, I think, a better analysis model.
Any more questions? Looks like that might be it.